Alrighty, what do we got cooking here? Number 8, at least it's experiment number 8 in 2019. So this is the typical layout, how it's often written, and the stuff that we see happening. The TLC that I have, basically the product when I ran it stuck to the baseline pretty good. But let's just get right to the IRs. So for IRs, I already assigned this one chalcone. You can definitely see that right here we've got a SP2 hybridized carbon with a hydrogen stretch. This one is likely to be the carbon-carbon double bond stretch, that one right there. The carbonyl stretch, I got it backwards, retract that, 1661 is the carbonyl carbon-oxygen double bond stretch. This nice peak at 1604, quite prominent, very, very likely to be the carbon-carbon double bond stretch. Be that one right there. And then as usual, the benzene ring, you can see one right here, along with this one. Aromatic C carbon-carbon double bond stretch. I don't really see much else in this region that's very diagnostic. This one, however, stands out as the mono-substituted out-of-plane bend aromatic stretch. And again, this is the characteristic mono, the classic 4 peaks on a slight angle down. That is the overtones mono-substituted benzene ring. So that takes care of that one. The other starting material is the acetoacetate or something like that. So right here you can see you've got sp3 hybridized carbons with hydrogen stretching just under 3,000, right? You can see what this IR kind of looks like. You get 2 absorptions right here. There's 2 of them. One of them, the one that's a little bit farther to the left, is the ester carbonyl. The acetone or ketone-like carbonyl is the one just to the right, the lower number. Then you have, this is not particularly diagnostic of anything. You might want to say it's aromatic, but there is not any, right? So there's no carbon-carbon double bond stretches here. The only thing you might be tempted to label is the carbon-oxygen stretch somewhere in here. But look at this multitude of peaks. To say definitively which one's which, I wouldn't even bother. Unless you know for sure, I wouldn't bother circling it. The product. So the product, looking like that. So the IR that I took, clearly this peak here, you really have to wonder, it's not part of this product. It could be leftover, for instance, ethanol, maybe, or moisture. But I would not label this peak. If you had to, I would say, if yours looked like this, I would say ethanol, perhaps, or water. But you can definitely look here. Maybe they're not peaked. These 2 peaks right here are above 3,000. Those are the carbon sp2 hybridized with hydrogen stretching. This peak here and that one, sp3 hybridized carbon with hydrogen stretching. And then we have also 2 carbonyls. One is ester, one is a ketone. The one at 1734-ish is the ester carbonyl. This one is the ketone one. The 1606, that peak there, and even this one on the side, the classic 3 carbon-carbon double bond aromatic stretch. Other than that, we could look at mono-substituted absorptions. And this one, you see there's 2 mono-substituted rings, and one of them has a side there, but you could at least circle these 2 if you wanted and say that's a mono-substituted OOP bend. And again, I don't really see any strong evidence of a carbon-oxygen stretch that's super obvious to be signed off on. So I think that's good right there. So we've done that. The starting material, I am missing the acetoacetate, or whichever you want to call it. I have the chalcone though. So you can definitely see that the chalcone starting material looks like that. Your final product, which is that one, should look basically like that. And what you're going to see is nothing absorbing into past 400. which makes sense because it's white anyway. So now we'll look at NMR. So what I'll do is I'll take a look at what already is posted. This was run on a 500 megahertz machine at University of Windsor. So you can see how this was a blown up region of this. I've already kind of numbered it. My point is each and every one of these carbons above the baseline is real. Okay, and that was run on a 300 or 500 megahertz. This is what it looks like. And I think you can already, this is posted on Blackboard, so you should still see the same one. All of these hydrogen peaks, they might start overlapping with each other, okay? Just remember that some of these peaks, like this was acetone, right? And this one right here, on the day I ran mine, was water. So these two do not belong, and that was indicated. So you run on ours, it looks like this. And I have this posted on the fridge or something, so I've already partially assigned it. I've already labeled this for you, right? So you can see how I've labeled it there. You can see how the aromatic, right? It's already labeled 10 hydrogens. I've labeled it G. You can't tell them apart. HF, right, is that one, right at 6.6. I've circled what looks like a quartet. See how I've kind of traced what it would look like, that quartet? Because when you go to this 500 one, you see the quartet would be isolated and right there on its lonesome. But our 60 megahertz crunches them together a bit, so that was B. And then this stuff, I've labeled it as position E, this stuff right there. This stuff is C or D, it's 2, it integrates to 2. Then over here, you're gonna see A, and what we have is leftover ethanol in this one. So a lot of us have problems with ethanol showing over top. All right, was left off to help somebody, a little bit of a glassware issue. So this year, as I was mentioning, this product had some leftover ethanol. So you could see the methyl group triplet was overlapping with the triplet. So A of our compound gives a nice triplet, and it's down here at 1.0 something-ish, right? So I've labeled that one as A, but so just watch out for that. So that's the proton. The carbon 13, I didn't write the structure on this one just because you can see when you run it with enough scans, you can clearly see the carbonyl, that's the ketone carbonyl. This one would be the ester carbonyl. And then you have the short, stubbier peaks. Chloroform is at 77. There's 2 peaks here. A couple more. Some of this is ethanol. The point is, all of the peaks can be found, and when you compare it to what was already posted on Blackboard for the carbon 13, you're going to see all of the peaks, and it's already been essentially labeled for you. All right, so the mechanism. So we can get this done as dead as a doornail. You guys should already be able to put this mechanism together because it's already in McMurray anyway. So I'm just slowly showing you the steps, right? Slow, methodical, takes a while, and then voila. The reaction energy diagram I've thrown together. So what I've basically done here is you have your starting material. Along the way, I got these other points. Your final product, I drew it being slightly higher in energy than the starting material. There's a lot more functional groups, so it's slightly higher in energy, allegedly. But you have other 2 things along the way. One of them looks like this, which is the Michael product. It's neutral, so that's why it's here. The other one is technically like an aldol with that OH before elimination, similar in energy to that. The elimination of the OH to make the double bond, right, is an SN. There's no intermediate for that one. But these other 2 steps, arguably there's an intermediate. One of them is the anion like that. The first step in the mechanism, this intermediate, has an anion there for the before the Michael product. So that would be the reaction energy diagram. At this point, I mean, you guys should pretty much know how this works. The NMR was pretty clean, so on the crude stuff. If I could have separated the ethanol peek, I could have made a slight correction. So my yield had a little bit of ethanol in there. I could definitely comment on that. The white color of the product, the UV absorption. So even though there looks like there's a lot of phenyl groups in here and double bonds, this conjugation that goes through here, surprisingly, is not enough to shrink the pi to pi star transition into the visible, because clearly our final product is white and the UV absorption does not show any amount tailing into the 400, past the 400 in the visible. So the extended conjugation here with the 6-membered ring is not quite enough, like it was for chalcone, to make it yellow. This one has no color, and that's the comment. We obviously would have to check the filtrate like always. We filter this, we get white powder. HPLC would be the best thing to check any leftover organic material. The TLC does not really show seemingly much of the starting material, although acetoacetate or whatever it's called doesn't really show up on UV very clearly. So HPLC would be needed to quantify all the organic material. And the other thing too is for yield, our starting material, most of us use it as crude from the previous one. So whatever mass you think you're weighing out for the starting material is not really accurate with what was actually there in terms of moles of starting material when you put it in the reaction itself. And there does not seem to be any evidence of leftover starting material when I ran it. So yet again, HPLC would be needed to clarify that. This is just the rough touching on what your discussion could be like. But that'll do it for number 8.